This is the 16.1, 16.2 notes for statistics honors. What you're going to find is there's going to be a little bit change of direction when it comes to the class and hypothesis testing in general. You'll notice that we are going out of order, which is of no consequence to you guys. Just realize that we are jumping from chapter 12 to 16, and we're going to make our way back to 13, 14, and 15. But the content is going to go in a much different direction, mainly because we're going to be moving away from symmetric curves to do some of our analysis. If you remember at the beginning of the semester, we talked about shape, and we talked about how we had symmetry for symmetric curves, and we had skewed curves. Well, now we're going to be jumping into how hypothesis testing can be used in a skewed distribution. Okay, so the first thing to take note of, returning to our section on the difference between two means. So what did we do? We essentially had a null hypothesis of mu1 equals mu2 and an alternative of mu1 is not equal to mu2. It could have been greater than or less than, but we're going to just stick to not equal to. So the goal is essentially we were comparing these based on their difference. So the next step is, well, what if we have more than two population means? What if we have 4 or 5 populations and we want to compare to see if the means of all of those populations are the same? So in other words, what if I did something like this? What if I did this? So if I have that scenario, then I go, all right, well, it makes sense that if I need to do that, it's not going to be just as easy as comparing 2 at a time, because can you imagine how much work that would be to run a comparison between mu1 and mu2, mu1 and mu3, mu1 and mu4, and so forth? It's a lot involved. So we wouldn't be doing that. So when we move to more than 2 population means in terms of wanting to compare them, we talk about what's called the analysis of variance, which is abbreviated ANOVA. Okay, it's a very popular statistical concept, and even more popular when you're doing data analysis, because a lot of times we want to compare the means for a lot of different populations, not just 2. So in that standpoint, we would use ANOVA if we went beyond 2 populations. In order to use ANOVA, we use what's called an F distribution. An F distribution, unlike many of the distributions we've seen before, are skewed distributions. So there is a similarity between F and T in the sense that T actually had infinitely many versions of its distribution, and what was it based on? It was based on the degrees of freedom. Well, the F distribution also has infinitely many distributions or variations of it, and it was once again related to degrees of freedom. But this time, F distributions actually have 2 different degrees of freedom, interestingly enough. So what are the 2 types? Degrees of freedom of numerator, degrees of freedom of denominator. So how do we show the degrees of freedom? Well, prior to this, if we had, let's say, the T distribution, I would just write degrees of freedom equals 8, right? Well, now we have to write it a different way because there's 2 different ones, so we write it like this. We would say degrees of freedom equals a set of parentheses, 10, 2, where the 10 represents the degrees of freedom of numerator, and 2 represents the degrees of freedom of the denominator. Both of these have an impact on what the curve looks like. You don't have to know those details, but they are used in order to determine the F distribution curve. So, for example, this is an example of a F distribution curve with degrees of freedom 950. It's tall. It's not far off from a normal distribution, it appears. Whereas if we go to a degrees of freedom 10, 2, like we had over here, it looks like this is a more classic skewed distribution that we would be looking at. So the key is understanding that each one of these curves is going to have a different set of area that revolves for a certain number. So I'll just give you an example. So if I want to know the area to the right of 1 in the shorter curve, that area, which is this, is going to be different than the area to the right of 1 in the taller curve. So each one of those areas is going to help us determine hypothesis testing, essentially p-values. So it makes sense, right? That would be the case. But those areas are going to be different based on the curves, which is why the curves are so important. Now, the other thing is, when it comes to skewed distributions, there is only one tail. This is much different than what you're used to with symmetric distributions, where you were talking about left-tailed, right-tailed, two-tailed. In these distributions, you will only be dealing with the right side of the curve creating a tail. Make sure you keep that in mind. It will be the same. There's another skewed distribution we'll be talking about in the last chapter, and it'll be the same thing. The tail is only going to be on the right side of the skewed distribution that we'll be working with. Okay, so the SF distribution, just like Z and T, has its own table of values associated with it. And you will be instructed to find a value of f in several of the problems that you do. So we first have to learn how to use the table. Okay, there's an abbreviated version of the table right here. I will get to showing you the whole thing soon. But the key is understanding that within the table you have degrees of freedom numerator across the top, degrees of freedom denominator across the side, and also values of alpha that are grouped in 5 different popular values. Now, why are these values important? Because if you remember in the t distribution, you'll see that there are 5 possible values at the bottom here, right? 5. So it's the same 5 alpha values, remember here, z sub alpha, that are in the table itself. So if we go, you'll see that they repeat the alpha values. So basically, this is the alpha value for all 9 degrees of freedom denominators. This is the alpha values for all 12 degrees of freedom denominators, and so forth. The degrees of freedom numerators are just listed across the top. So basically what we're going to do is we're going to do an abbreviated version of a problem, and then I'm going to show you how a little crazy it is when you go and use it in the bigger tables that we're actually going to be using. Okay, so just to be clear, remember, these values here are f sub alpha values. In other words, if you remember from z, when we did z sub, let's say, 0.01, that would be the z value with an area of 0.01 above it. Okay, that's when you do subscripts, it always means above. So we're doing the same thing here, and it's logical because all areas for what we're going to be dealing with in the F distribution are above because of the skewed distribution. So we're doing an example of f sub 0.05 with degrees of freedom 412. So this curve over on the right over here is a degrees of freedom 412 F curve. So what we do is we just find an area over on the right to mark an F value. Then we're going to write f of 0.05, which means we're going to mark the area to the right of it as 0.05. So what I need to know is what is the area of f that represents in this curve where the area will be 0.05 to the right. So our goal is to use this table in order to figure that out. So what do? Across the top, you can see the degrees of freedom is 4 right here for the numerator. Across the side, we have a 12. So the only thing we need to do is find the area to the right, which is our values of alpha. So in this grouping right here, it appears that the key value is 0.05, which represents f sub 0.05. So what do? Well, just like we always do, we follow inwards until we get to 3.26 as the value of f for our problem, 3.26. This will be an important thing that you'll have to learn in order to run your ANOVA test. Okay, so what do the actual F tables look like as a whole? So we've seen an abbreviated version, obviously, over here, but what does it look like as a whole? So let's bring those up. So there are many, many pages with the F distribution. We basically can go through and slide, so you can see them, there's a ton of them. So they go on for a while. Why is that? Because we have varying values for DFN and DFD. So we have to be able to cover all of those values. So for instance, in our scenario, we had degrees in freedom was 412. So would this first page give us what we need? Well, we see the 4, but if we go down for DFD this way, it only goes to 8, which means this page is not what we're looking for. So we have to find the page that would have 4 and 12 on it. So we go to the next one, and we see, oh, well, across the top, we've already moved away from the 4s, and they've become larger, but we're still from 1 to 8 on the right over here, so that's not it. So if we move over to this one, we go, okay, we're back at 4 for what we're doing here, 4. And hey, there's 12. Oh, and there's 0.05, which means, again, if we go in, down in here, it looks like we're going to get the 3.26 that we actually were looking for to begin with to do our problem. So the key is understanding that you might have to do a little bit of legwork in order to figure out how to, to get these values. It's not always going to be super simple. You just have to find the correct spot on the chart where everything is going to exist. Whereas 16.1 concentrated on how to use the F table for determining critical values of an ANOVA test. This section is going to talk about the logic of how an ANOVA analysis. So you're going to learn more about the actual test itself and how different it is from some of the other things that we did. For example, basically in ANOVA, as we spoke of in the previous, earlier in the lesson, you're going to be talking about comparing means of a single variable for several populations. So instead of just 2 populations comparing to one another, you're going to be doing more than 2, 3, 4, 5, whatever it is. Could be 50. But you're going to be comparing the means for several populations. I stated how we're going to be using what's called a one-way ANOVA. So what's unique about a one-way ANOVA? Basically, that it's going to compare the means of the variable populations for the result for one other variable. Just one. It's called a factor. Okay, note that if we had gone beyond one other variable, it would have been called a two-way ANOVA, but that is not something that we do in this class. So we're only going to be doing for one other variable. Now note that the variable of the factor variable, whatever the factor is, can be broken down into levels. That's not super important. That's just like a vocab word, but that's essentially what we're going to be concentrating on. So let's just give this a face a little bit. So I'm going to read this. It says, for example, suppose that the variable under consideration is household energy consumption. And there are 4 populations. So essentially you have Northeast is one population, Midwest is one, South is one, and West is one. So these are your 4 populations that you're going to be dealing with. So basically, the factor is region. Okay, it kind of makes sense in terms of what we're going to be working with. And that means that our factor has been broken down into 4 levels. The levels are Northeast, Midwest, South, and West. Just so that we're using the terminology the way it's meant to be. But in general, all you guys really have to concentrate on is that we have 4 populations that we need to run what's called a one-way ANOVA on in order to determine if the mean household energy consumption is the same for each of the 4 regions. That is going to be the key concept in terms of the beginning logic of an ANOVA. So I had stated that the two-sample t-test was basically comparing two means, whereas ANOVA's more than two. Well, it turns out that the two tests have the same exact assumptions, essentially. So if you look at the assumptions here, what do we have to make sure? We have to make sure that the samples taken from in this case, 4 populations, are all simple. You have to make sure they're independent of one another. You have to make sure that you're going to get a normal population out of this. So ideally, we'd like to take more than 30 independent random samples from each population. And we're back to this again. Ideally, we would like equal standard deviation. So remember, equal doesn't mean the exact word that you think. It means approximately equal. We talked about pooled standard deviations back then, but we don't have to worry about really that now. It's just about all of them are similar standard deviations. And if you recall, the rule of thumb is that one cannot be twice another within the scope of using that as a check for assumptions. Alright, so let's continue a little bit with the logic here. This is a little bit challenging, this next concept, but it's just about kind of understanding the difference between things that affect the difference between sample means. So if you look at this picture, basically what we have is dot plots from a sample from each population we're dealing with. So let's say we have population 1, in which we take a sample and we end up, it looks like 1, 2, 3, 4, 5, 6 data points. Their mean is 20. Okay, we have another population here, population 2, in which we have another group of sample in which the mean is 25. So if we're normally running a test, we're trying to use a hypothesis test to determine whether these means are the same or they are different in terms statistically. That is the goal usually whenever we're doing any type of hypothesis test. Okay, so how do we know if they're different? That's the key. Okay, we're trying to figure if there's a clear difference between the sample means. So in order to do that, there's actually two concepts that are at play. We're trying to determine if the difference between the sample means is either the pure difference between the population means or the variance within the populations. These are the two concepts that are going on here. So if it's clear that one is obvious than the other, then that would lead to essentially a rejection. If it's unclear, then it won't. That is kind of a weird concept, but literally the best way to think about it is if I'm looking at these two dot plots, I cannot look at this and go, wow, like, let's say I didn't know what the means were, and I just looked at this. Would you know that the means of these two dot plots are different? So is this, the difference between these sample means, is it due to the difference between the population means? Or is it due, or the variance within the population? So when variance means how spread out the data is within the population. And when you look at this, there's no way to really tell whether the means are different or not by looking at it. But if you go to a completely different example, let's say that we have the same scenario where we have population 1 with a mean of 20, but this time this is your dot plot. Let's say you have population 2 with mean 25, and this is your dot plot. If you look at these two pictures, it should be pretty clear that these means are going to be different. And they're going to be different due to the difference in the population means. Why? Because these are all clustered around one value, while these are all clustered around another one. Which means it is very clear that this has nothing to do with the variation within the population. It has to do strictly with the difference between the population means. Which means this is a scenario where we would reject H naught, because the means are clearly different. But if you look over here, you go, I can't really determine that by what I'm seeing right here. So that is sort of the logic of this. So just sort of a summary, it says, I'm going to read it. So it says, in summary, if the variation among the sample means is large, relative to the variation within the samples itself, conclude that the means of the population are not all equal. Okay, this is a very wordy statement. I know it's very difficult, but as we go through and derive how to find the variation among the sample means, how to find the variation within the samples, you'll get an idea of why this is the logic that we're going to use. So luckily, we actually have measures for this. So right here it says, as a result of this conclusion above, we will need 3 quantitative measures. Again, the variation among the sample means, the variation within the samples, and then we're going to need an objective value for deciding whether the variation among is large relative to the variation within. That's going to be these values right here. So what we're going to be doing is we're going to be using these as the actual values we're calculating. So in terms of the course, yes, it's ideal that you know all of these concepts and what they mean, but in reality, you're going to be calculating most of them. That's going to be the key. So as I go through, I'm going to try to go back to the logic up here and talk about it a little bit, because I know it's a stretch sometimes for students to really put this in their head. But in reality, the key is calculating these and understanding what they mean. So the first one here is called the treatment mean square. It's MSTR. So this is the measure we're going to use to determine the variation among the sample means. Okay, so within that formula, we're going to have, and you can see the formula is actually listed right here. There's going to be a lot involved. For example, we're going to have to calculate what's called the SSTR. We're going to have to find the value of K. These are things that you don't actually know of yet. We'll get there. We're also going to have to calculate the error mean square, which is going to be the value that represents the variation among the samples. And if you look at the formula for such things, this is also going to be its own formula, where we're going to have to calculate the SSE and know what N means in order to do that. So we got a lot of formulas going on here, which all will be broken down very soon as we go through examples. But one thing I want to talk about first is this. So if you look here, this is called the F statistic. So F represents the ratio of the variation among the means to the variation within the samples, or in other words, the ratio of MSTR to MSE. So remember, the key was, if I go back to my statement right here, in summary, if the variation among the sample means is large relative to the variation within the samples, so that essentially is F. So if this is large relative to this, then F is going to be large. If F is, remember F is this, right? If F is large, that means it's going to be all the way out here, which means the area to the right of it's going to be very little, which means if we compare it to alpha, we're going to end up rejecting H naught, and the populations will not be equal. So yes, that is very wordy, and yes, we're early on in this, but what that does is give you an idea of how the ANOVA actually works. So in the beginning here, you know what the goal of all of this is. And just also to bring this back in, remember, we're going to be using the table value of F, essentially the F critical value, in order to determine whether this F is larger in a critical value method, whereas I was talking about how the p-value is lower, which would be the p-value method. So again, just like every other test, we're going to have different ways to actually do this. So right now, you're either hopelessly confused, you're going, okay, I think I kind of get it, or you definitely get it. So no matter where you are with that, it's not a big deal. Ideally, we're going to now talk about how to compute all of these things, and we'll eventually do a lot of examples in order to make sure that you are clear on this. Okay, so what about these formulas that you have here? So you'll see up here that we have to calculate MSTR. Now, MSTR has two variables in it. It has SSTR and K. So let's sort of, first of all, talk about SSTR. It says in order to compute MSTR, you will need to compute SSTR, which is the treatment sum of squares. Okay, the formula is right here for computing it, and what you'll find is it's a lot like standard deviation from the standpoint that you're going to have to likely come up with some tables and do these calculations. So, for example, the subscripts represent the population number. So what are the values here? So you have the sample size taken from the first population. You have the sample mean of the first population. And then you have a new value that's just X bar. Now, it doesn't look new, but it actually is. So it's actually called the grand mean. Okay, the grand mean is the mean of all the samples, and we'll talk about how to calculate that in a second. Worth noting that more familiar to me, they usually call it X bar bar. Okay, I know that sounds kind of weird, but they do X bar bar. So they do two bars on top of each other. Now, if I don't know if they do it in this textbook or not a big deal, but worth noting, if you tried to look this up, it's probably going to be X bar bar. But it's the mean of all the samples, essentially, that you're going to find. And the reason why you know it's different than the other X bars is it doesn't have a subscript. Now, if you go to the other values, you're going to see that it's just going to repeat. So sample size of population, the sample you're taking from population 2. The sample mean from the sample you're taking from population 2. And again, the grand mean that's in here. And all you're going to do is find that for every population and sample, and then you're going to end up adding them up to get SSTR. Okay, there's a little bit of a typo here, so just get it. So right here, this should say SSE. So it says in order to compute the mean square error, you're going to need to use the sum of square errors, which are the error sum of squares, a bunch of ways to say it, in order to calculate that. So here, again, formula. So from the first population, you're going to take a sample size. You're going to subtract 1, and you're going to multiply by the variance of the first sample, which is the same as saying the standard deviation squared of the first sample. So you're going to be doing that for every population and sample, and then adding them all up to get the sum of square errors for doing that scenario. So these are going to be the formulas. We're obviously going to do it together, so no big deal. And then we're going to be taking each of these numbers and dividing by variables involved with K and N. We will talk about that in 1 second. Okay, let's talk about an example right here. It says the Energy Information Administration gathers data on residential energy consumption and expenditures and publishes its finding in a survey. Suppose that we want to decide whether a difference exists in the mean consumption of annual energy by households among the 4 U.S. regions. Okay, so when they say that there is a difference in the mean among 4 regions, you immediately know it has to be ANOVA. If I asked, is there a difference in the mean among 2 regions, then you would use a 2-sample t-test, ideally. But because this says 4 regions, we immediately know we must use an ANOVA. Okay, so let's talk about that. So notice they do give you an alpha again, so same as always. So let's look at our data. So we have the household expenditure, consumption, household energy consumption values for each of the regions. So you'll see that we have 5 for the Northeast, we have 6 for the Midwest, 4 for the South, 5 for the West. I've also calculated the means for each one of the regions. So 11 is the mean of these guys, and 12.5 is the mean of these guys, and so forth. So we have already some values that are of importance here, so we are good to go there. We're going to start by letting the 4 means denote last year's energy consumptions by household in our 4 regions, which is our factor. So what are the hypotheses? What do they look like in an ANOVA? Well, the null is going to look very similar to the 2-sample T, except there's going to be 4 of them. So it's going to be signifying the means are the same. So mu1 equals mu2 equals mu3 equals mu4. So by the way, in textbooks, other textbooks, just like I've spoken of before, they would use, let's say, N, M, S, and W instead of the subscripts 1, 2, 3, and 4. So it would be like mu sub N equals mu sub W, M equals mu sub S equals mu sub W. So worth noting, this textbook doesn't do it, but I figured I'd mention it. So the alternative, we're not going to write the same thing with not equal signs or any inequality symbol. Instead, we're just going to always write the same thing. Not all means are equal. So, there's a key thing here going on though. When they say not all means are equal, the best way to really describe that is that at least two of the means differ. So that's kind of weird. And it's kind of the understanding of this that's really important is, in reality, a couple of these could be the same. But the goal is if only one of these is different than another one, then automatically this test is going to fail. So there are some limitations to this, which we'll deal with later, because we're going to have methods for determining which ones made it fail, but in reality, you're never going to know that in the beginning. You're literally just going to get some value for either your test statistic or your p-value that's going to lead to rejection or non-rejection. And if it rejects, that means that at least two of these are not the same as one another. We don't know what that is yet, but it could be that all of them aren't the same, but all we need is two of them in order for this whole thing to blow up and reject H0. Okay, so let's get into those mini variables that we talked about. So first things first, the variable k. So k represents the number of populations. So how many regions do we have? We have 4 regions. So k will always represent the number of mu's you have in the null hypothesis, or in other words, how many populations there are. Okay, n represents the overall total number of observations. Okay, so what do they mean by that? They mean each one of these numbers is an observation. So what you have to do is count them out. So let's say for this one, n1 equals 5. For this one, n2 is equal to 6. n3 is equal to 4. n4 is equal to 5. So in order to find this value, we have to do 5 plus 6 plus 4 plus 5, which gives us 20 as our value. Okay, lastly, we have the grand mean. So remember, I mentioned that this is often x bar bar. In your textbook, if it isn't, it's not a big deal, but it's more commonly seen as x bar bar. So this is the grand mean, and you have to be really careful here. So what do you think a student would do in order to find the grand mean? They probably, did I say grand mean? I'm like addicted to bar bar. So no, it's not the grand mean. It's just the single grand mean. So if you look at this, we have 4 means, right? So what do you think a student would do to find the grand mean? It seems logical. They would probably add them all up and divide by 4. The problem is you cannot do that. You could do that if there were 5 values in each one of these, but because the n's differ, that means you cannot do that, which means there is going to be a formula we're going to manage later to help us with that. But for now, what do you need to do? You have to add up all of the individual values all together. If you do that, you're going to get 196, and then you have to divide by how many there are. Well, we already know there are 20 from over here. So if we do that, we're going to get a grand mean of 9.8. So that is the average energy consumption among all of the regions separately, individual households. Okay, so next we have to determine how we actually find the treatment mean square. So let's just return here. Let me get a big fat eraser and get rid of all the noise here. Alright, so what was the goal here? In order to calculate MSTR, we have to use this formula. Okay, note, we already know what K is. It's 4. It's the number of population. So if we could calculate SSTR, then we're going to know MSTR. So they told you down here that SSTR is actually this formula here. So generally, we need to calculate this value right here for every single population. So that's what we're going to do. So we're going to head down here, and you'll see that the last value is exactly that value. So what do? Just like we did with standard deviation and all the other things that use tables for calculations, we're going to generate that value slowly as we go through the table. So I often call this the SSTR table, and you're going to have to learn how to use this. So our first variable we need is n. So we need the sample size for each region. So note I already did that. It's 5645. So we put it in, right? We're also going to need the mean for each value. Well, that was also calculated for you. It was 11, 12.5, 7.5, and 7.2. So 11, 12.5, 7.5, and 7.2. Okay, now, what does this say to do? So remember, an x bar without a subscript is the x bar value, the grand mean. So luckily, we calculated that already. It's 9.8. So that's going to be that value. So we need to take every single one of our means here, and we need to subtract 9.8. If we do that, we're going to get 1.2, 2.7, negative 2.3, negative 2.6. All right, so we move on. So remember here again, looks like all we're doing is taking the previous column and squaring it. So that's what we're going to do, and we're going to get 1.44, 7.29, 5.29, 6.76. Remember, all values squared become positive. So that means the only thing left to do in order to find our result here is to take our first column, n, and multiply by our fourth column, x bar sub j minus grand mean squared. So this is going to be, just to be clear, so this first one's going to be 5 times 1.44, which is going to give you 7.20. And this one is going to be, the last one I'll do, 6 times 7.29, which is 43.74. So if you continue on and do the same process, you're going to get the following numbers, 21.16 and 33.80 as our value. So if you look at this, you obviously have the values for each individual. So let me just get out the noise here again. You have your values for each individual one of these. So just remember, in order to find SSTR, what do we need to do? We need to find the sum of all of them. So that means, just like we've done in the past, we need a summation column here so that we add all of these together and we end up with 105.90 for our value of SSTR. SSTR. So, what was the goal of this? The goal of the get STR was to calculate MSTR. What's the formula for MSTR? It is SSTR divided by k minus 1. So we're going to take our 105.90 and divide by k, which is 4 populations, minus 1, which is going to be equal to 35.3. So right away, that would be the first step of the process. And to be clear, that is going to be the numerator of our F statistic. So the only thing left is to find the denominator of our F statistic, and that'll be what's up next for what we're going to go through. Okay, so now we have to find the error mean square. Okay, that's the denominator of F. So just like we talked about here, so let's go back to the logic here. So the error mean square requires that you calculate the error sum of squares. This relies on the formula MSE equals SSE over n minus k. We already know what N and K are, so we have to find SSE. So what did we do? We came down here and we determined the formula. The formula was essentially finding this value right here for all of the populations and the samples you take from them, and then adding them all together. So again, we're going to go to our table, our new table. So this is going to be the SSE table. And we're going to use our variables that we know in order to generate this expression. When we're done, we're going to take the sum of it, and that is going to be equal to SSE. So that is the goal of the problem. Now note, in a lot of times in these problems, the variances are given. Why? Because the variance is a key part of the SSE calculation. And if you look back at the data, we don't have anywhere in the given information here anything about the variance of, let's say, these 5 values right here. Hold on. These 5 values or these 6 values. We don't have that. So that means that would have to be calculated. We don't want to spend time doing that by hand. So that would be calculated with statistical software. I did it for you, and they are right here, which means we can actually, if you want, throw those right in right away. 3.5, 6.7, 9.0, and 3.7. We already have these sample sizes. They were listed here, 5, 6, 4, 5. So we can write those in. Okay, this column is just taking n minus 1, so 5 minus 1 is 4, 6 minus 1 is 5, and so forth. So, believe it or not, this one is actually much easier to calculate. There's not as much going on. So in reality, the last column over here that we have to find is just about taking the first column, not the first column, hold on. It's the only one we're not taking. It's about taking the second column and multiplying by the third column. Okay, so as long as you do that, then you'll be able to do it. So I'll just give you an example. So like this first one right here, we're taking 4 times 3.5. Right, 4 times 3.5, and that's going to give us 14. And for the next one, we're going to do 5 times 6.7, and that's going to give us 33.5, and so on, 27, 14.8. These are all the values for this, and then just like we spoke of at the bottom of this page, we now need to find SE. We have to take the sum of all of those. So in order to do so, we're going to get, add these up, and we're going to get 89.3. So 89.3 is going to be our SSE for the problem. We then can calculate our MSE, which has a formula of SSE over n minus k. So we can take our 89.3 and we can divide by n minus k. Well, what is n in our problem? So if we return to, again, let's get rid of the noise here so you can remember. So if you recall, we had 4, 20, and 9.8. Alright, so if you look at our values that we're looking at here, we have n, which is the sum of all the samples in the entire chart here, and then 4, which is the number of populations. So we're going to do 20 minus 4, which is going to give us 5.581. So 5.581 is officially the denominator of our test statistics. So if we go back to F again, just to be clear, that was not what I wanted to do. Back at it. So if we go back to F here, we're basically looking at this guy. This is the formula right here. So MSE is the second guy, the denominator that we're working on. So when's all said and done here, we can take our values of MSE, so MSE is down here, and we can take our value of MSTR, which we calculated here, 35.3, and we can get an F of 6.32. So essentially, in an ANOVA, we're going to be saying, is this value of F large enough to reject H naught? Why do we say that? Because we have our skewed F distribution, we're going to, 6.32 is going to be someplace out here, and we're going to say, is that far enough out into the tail for us to decide whether we reject H0? What are the two methods? We have a critical value method, so we're going to find an F critical value from our table. We're going to determine if 6.32 is to the right or the left of it. Or we're going to take 6.32 and find the area to the right of it, which is the p-value. Either way we do it, we want to know, is F large enough to determine that? And if you remember the logic of this, what they said was, if MSTR is large relative to MSE, then we're going to reject H0. But the scope of large, the magnitude of how we distinguish large is the key. Is 6.32 large enough? Well, that is going to be the concept of the test. We're not going to do it right now, but this gets you started with how you do all the calculations, and we'll return to this in the next lesson so we can determine whether we reject or do not reject H0. And remember, H0 is that the means are all the same.